Okay, so this is a video tutorial for team challenge number 10 on enzyme kinetics. Now, what I've set up here on the board, I copied the data in purple that was given. And what I've done is I've calculated the reciprocal, or 1 over that number, and put that in green here. So that generally is the first step when you're going to do a Lineweaver-Burk, is to take the reciprocal of all the data. Now, when you're going to plot for Lineweaver-Burk, don't look at all the points that come after the first ones. The first ones, being the smallest numbers, are going to give you the largest reciprocals. So when I'm doing this, I force myself to actually put my axes on the graph before I even look at the other data. So I've put a little graph here. It's not very fancy. Note, you don't want the y-axis over here on the left because the x-intercept is going to be important. So I put the y-axis about 1/3 of the way along. Okay? Now, I have to get as high as 0.4 on my x-axis, so I'm going to evenly, not logarithmically or strangely or nonlinear, but evenly space that along here. So I've got 0.1, 0.2, 0.3, and 0.4. Likewise, I could go negatively, and negative 0.1, negative 0.2. Now on my y-axis, I've got to get as high as 0.04. So I'm going to divide that evenly, noting that a lot of these points are going to be really tiny, and I'm going to call that 0.01, 0.02, 0.03, and 0.04. Now it's going to be really hard to plot this nicely without any grid lines, but I'm going to do a try at it. So the idea is to plot the data as best you can. So I've got the value of 0.4 over here and just over 0.04 up here. And then I've got 0.2 lining up with 0.021 somewhere in here. I've got 0.1 lining up with 0.011 somewhere in here. 0.05 lining up with 0.006, so somewhere about in here. This is going to get really tricky on this graph because I don't have grid lines, but anyway. 0.025 lining up with 0.035, somewhere in there. 0.0125, really getting close over to the axis here. I'm going to leave off the last point because I can't even fit it on there. And then I'm going to draw a line of best fit through those points, remembering that this is perfect data right now that I've given you. It all exactly fits the math. When you actually get this data in the lab, which you do in second year, it's not perfect. It doesn't all fall in the line. So you do have to get the line of best fit if you're going to do it this way. So what I need to know from this is my y-intercept, 1 over v max, which is really hard to estimate from this graph, but it looks like it's somewhere down around 0.001 or somewhere in that range. And the x-intercept is negative 1 over km, and that seems to be coming out at about negative 0.02. I say about, this is pretty crappy plotting. Okay? The actual values then can be gotten from the reciprocals of these, and I did them out on Excel. The km works out to 97.7 micromolar, and the Vmax is 973.9 micromolar per minute. Now the next part asks you for a kcat when you have, this is for data with 11 nanomolar enzyme. So my Vmax here, 973.9 micromolar per minute. I'm going to have to do some unit messing about here. I suggest one of two things. Take it to molar or take it to nanomolar. I'm going to go to nanomolar and say there are 1,000 nanomolar in 1 micromolar. It goes milli, micro, nano, pico. So I'm going to say there's 973,900 nanomolar per minute. All right? Divide that by 11 nanomolar. That's going to give me a number, which I don't know what the number is off the top of my head, per minute. I'm asking for the kcat per second, so I want to divide that number by 60, okay, seconds per minute. All right? And that will give me the turnover in 1 over seconds, which is 1,475.6 1 over seconds. So that's how you do the kcat. The final part of this question asks for the V naught when you have a different enzyme concentration. In this case, it's 31 nanomolar, and a concentration of substrate equal to 66 micromolar. I'll let you do the math yourself, and I don't even have the math calculated out here. But what you need to do is calculate a new Vmax. Because this value here, this kcat value, down here, this is a constant parameter for that enzyme. So to get a new Vmax, I've got to use my Vmax equals kcat ET, ET times kcat, to figure out my new Vmax. So I will use this enzyme concentration and the kcat from down here. This will give me a new Vmax. And then all I have to do is plug the concentrations and the Km and the Vmax that I have into the Michaelis-Menten equation. Vmax times S over Km plus S. So I just plug all of that into the Michaelis-Menten equation to get the velocity at that particular enzyme concentration and substrate concentration. Just bearing in mind that Vmax is dependent on the enzyme concentration. So if I'm changing enzyme concentrations, I've got to calculate my new Vmax using this kcat that I determined and my new ET. So that's how you do that type of enzyme kinetics problem.